Hello, everybody, and welcome to the virtual seminar series on Bayesian decision making and uncertainty. And we're super excited to have everybody here. Thank you for joining us. My name's Alex Trennan. I'm with Cornell and one of the organizers who's going to be hosting today's event. And I'd like to take my fellow organizers, Renato Berlingeri, Natalie Mouse, and Zi Wang for their work in helping put this series together. And before we get started, and with apologies for the slight delay due to technical issues, I'd like to just make a few announcements. First off, following this seminar, we've got amazing lineup of speakers in the coming weeks, and you can find the schedule for this on our website, which is gp-seminar-series.github.io. And yeah, check it out. You can join seminars via Zoom, provided you register on the Google group to receive emails with the links, which can be done on the website, or you can always join via YouTube, which does not require any registrations. Seminars take place at 1600 UTC, which is Coordinated Universal Time, and we just had a daylight savings change, so be on the lookout for that. If you're joining us via Zoom, you can use the raise your hand option to ask questions, or you can type your questions in the chat during the talk, and the speaker can choose to pause and answer questions or hold them to the end, depending on their preferences. And with all of this said, I'm extremely excited to introduce Frank Hutter with the University of Freiburg, who will give today's seminar. Frank, the floor is yours.
All right, thank you very much for the invitation and for the kind introduction. I hope you can see my screen now.
Not yet.
It worked earlier. Can you see it now?
Yes.
Okay, good. Let me just find the chat window. Okay, so if you have questions in the chat, I'll also see that. Yeah, without further ado, I'll get started talking about this work on TabPFN, but seeing that this is the Bayesian decision making and uncertainty seminar, I'll also focus quite a bit on the PFN part behind it, because that is closest to Bayesian decision making and Bayesian optimization. All right, but the talk is a lot also on tabular data. And so let me start with answering the question that people always ask me: why tabular data? Why not vision, speech, etc.? Why tabular? Well, it is a very common problem that is often underrated. One type of tabular data is in time series forecasting, which is very easy to visualize like this. You have a time series, and at some point you want to predict the future. And there's lots of applications of this, like how will X develop over time, with X being stock prices, energy prices, income and expenses, demand, inflation, etc., etc. So very easy to see that that is something that comes up often. But the more general tabular data prediction problem comes up even more frequently. Here's an example of one of the types of tabular prediction problems that I'll be speaking about, where you have columns and you have rows. A row in this case here is, for example, a patient. You have a particular type of column that you want to predict. In this case, does this patient have early stage Alzheimer? You don't know this for these new patients. You can wait a couple of years and then you know whether they had early stage Alzheimer, but then it's too late to actually treat them. And so you want to know whether they have it right now. So that's a tabular prediction problem. And indeed, personalized health models are a long-standing challenge. And you can do this sort of stuff with omics blood markers instead of invasive diagnostics. And there's many billions being spent on data acquisition right now. And it comes down to tabular machine learning in the end. There's lots of other examples, like, will this customer churn, or is this payment fraudulent? Will this credit be paid back if I give it? Which product does this customer buy? Will this treatment work for this particular patient? And I could go on and on. There's literally thousands of possible applications. This is sort of machine learning 101, the stuff you fit random forests to, etc. That's a topic of this talk. Why do we care about foundation models for this tabular data? Well, because in traditional ML, you have this training stage for every individual data set that leads to individual siloed models and lengthy task-specific training and hyperparameter tuning, etc. And in foundation models, well, you have lots of these data sets, and then you fit one foundation model to them, and that foundation model that is trained once offline, and then online it can just be used off the shelf without retraining, and it can also quickly be fine-tuned to new use cases. Right, and the vision that we have is that basically we revolutionize tabular data just the same as text and images have already been revolutionized by deep learning, whereas in tabular data, really, we're using methods that are 20 years old, and it hasn't been hit by the deep learning revolution, but this is about to happen. This is about the time where we're having the ChatGPT moment of tabular data. Yeah, and our community is on its way to revolutionize this tabular data. So we had this publication in Nature on TabPFN v2. That's a method that's more accurate than previous machine learning methods on like over 96% of the use cases. Methods like XGBoost and CutBoost, etc. This tabular foundation model is more data efficient than previous machine learning methods. So it only needs 50% of the data in order to get the same accuracy that the next best method actually gets with the entire data. And the method already has over 1 million downloads on PyPI, over 3,000 stars on GitHub, was released in January this year, and yeah, is used at a lot of different companies. So relating it to LLMs, language models, tables are the language of business, enterprise, and science, etc. Just think Excel spreadsheets and databases. So you have application areas of finance, healthcare, business analytics, insurance, lots and lots more. But focusing on these four for now, there's also different types of applications, in particular, good old classification regression problems, time series forecasting problems, and recommender systems. And well, one particular one we saw before, where we have this tabular prediction task in healthcare. If we look at what previous methods we're doing for that, we actually have big problems in or a lot of things that could be improved compared to previous methods. For example, there's these free-form features here that are just not being properly leveraged by methods like XGBoost. If you have missing values and you need to treat them somehow, do some missing value imputation, you have column headers, there's no semantic problem understanding in typical tabular methods. And there's lots and lots more issues. Maybe the one to highlight still is the transfer across data sets is just non-existent with something like XGBoost. You just train it separately for every new data set. Whereas, of course, we would like to have positive transfer, which is very common in deep learning methods. All right, so that is motivation for why do we want tabular foundation models. Next, I'm going to talk about some background on prior fitted networks, which is sort of the underlying math and the underlying methodological piece that makes TabPFN work. This is also applicable to other modalities. Then I'll talk about TabPFN, so applying PFNs to tabular data. There was a paper from 2022, and then TabPFN v2 is the new version of that just appeared in Nature. Then a quick bit on how this can be applied to time series and TabPFN TS, and then actually some fielded use cases and some extensions we're working on. All right, let's jump right into PFNs. So this was a paper called Transformers Can Do Bayesian Inference at ICLR 2022. So, well, this is a GP crowd. You know these pictures. You have a prior over functions, and then you have some function evaluations, and you have a posterior over functions here, just samples drawn from that. And, well, it's intractable to compute this posterior exactly. But what we do in PFNs is we actually jump directly to the posterior predictive distribution. So we only want the distribution at one x at a time. So we basically have this posterior, we integrate over the sensor noise and just directly get this posterior predictive distribution. And we don't do that with variational inference or Markov chain Monte Carlo or any other way, but we do it in a forward pass of a transformer. All right, how do we do this? Well, let me illustrate this first. So let's say we have this prior over functions, and then we sample from this prior, we sample different functions. And then for each of these functions, we sample some data points and call some of them train, the blue ones here, and some test, the orange ones. And we do that for each of these functions. Actually, there's going to be a lot of these functions. This is all synthetic data. We can do this arbitrarily many times. So that is one assumption that we have. We need to be able to sample from our prior. And if we can do that, then we can now fit a neural network that actually, given the blue points and the x axis of the orange point, predict where the y value of this orange point is. And once we can do that for millions of functions and samples from these functions, then we have sort of learned what this prior looks like. And given some actual data, and here a question mark, we can do a forward pass and actually get a posterior predictive distribution for this point. And so we have thus meta-learned to approximate Bayesian inference purely by doing supervised learning of data that we generate from our prior. And we can do that whenever we can sample from the prior. All right. This actually works, and it works arbitrarily well. I will talk about how I represent the posterior predictive distribution, which is a question in the chat. But so this works really well, actually provably exactly in the limit when we actually really reduce our cross entropy loss as much as we can, then we actually get to predictions that mirror, in this case, the exact posterior Gaussian process. You see there is some blue curve and a green curve that are slightly different. So if you train a little bit longer, then they get even more similar. Written in a bit more math. So we sample prior data sets from a prior. These are the data sets. We train the PFN by minimizing the cross entropy between our predictions and the true data. And then we have a PFN with parameters theta star, and then comes in the actual training data set and test input. And here we apply our predictive distribution with theta star, and that actually approximates the true Bayesian posterior predictive distribution. All right. The model that we use is a permutation invariant transformer. So it's like a transformer, but we just drop the positional embedding in order to actually treat the data as a data set rather than a sequence. And we also, importantly, for the Bayesian optimization crowd, we do not model correlations between outputs. So we do not have we can't model a covariance function. If we want to draw joint samples, we would first draw the x4 given this context, or the y4 given the x4 given this context, and then draw again given this context, including the y4, we would draw x5. So we don't get a joint predictive distribution for two outputs at a time. The way that we represent this is not as suggested in the chat as a Gaussian with parameterized mean invariance, but actually as a histogram distribution with something like 10,000 different bins. And basically you look at the input data, you push it through the model, you see where a lot of the prior data goes, that and the binning is adaptive to where these prior samples are. Um, we also, like the edges of this histogram distribution, we make half Gaussians to not have zero probability for anything. All right. Yeah, this can approximate more complex GPs. It's much better than what was previously there as attentive neural processes. And yeah, generally just works quite well. In particular, it scales. So longer training makes it better. So here we have a true posterior GP in purple. This is a number of data points in a data set. And the colors are different PFNs trained for a different amount of time. So this is trained with 500,000 meta data sets. This is trained with 1 million, 2 million, 4 million, and you get ever closer to the true GP. And of course, all of these curves, the negative log likelihood goes down as the number of data point goes up. So more data is better. And well, more data is not always better. At some point, we actually hit a computational barrier, just like GPs. GPs are cubic, and there's some approximations. And this here is quadratic. And because why is it quadratic? It's quadratic because of standard attention mechanisms used in transformers. And of course, you can also use different approximations, linear attention, etc. But then it doesn't perform quite as well. All right. So far I just showed, well, GP approximations. GPs are easy. There's a known posterior, but we can do better. We can do cooler stuff with this. It's really flexible. In particular, if you have a GP with unknown hyperparameters, then you would have to do maximum likelihood estimation or sampling, which is, for example, this no U-turn sampler. And there, actually, with the same number of data points, PFNs are better than these techniques, and they're just a lot faster. So eventually, if you run variational inference or MCMC to convergence, then they give you the optimal performance here. But this the PFN is here like a factor of 10 to the 4, so 10,000 times faster to get to the same result. And this is for small Bayesian neural networks, like literally really small, like 3 features or 8 features, 2 layers, a hidden dimensionality of 5, so that you can actually run MCMC and variational inference. But the PFN actually doesn't care about how big the latents are, because it just never represents a posterior over the latents. It only represents this posterior predictive distribution. It also enables other stuff. So we just showed this, the posterior predictive distribution for a Bayesian neural network that is like an MLP here. But you can also actually do things like as a proper Bayesian, you would like to actually quantify the uncertainty in all of the properties of your system. And it's not just the weights of a fixed neural network, but you also don't really know the right neural network. So you should have an uncertainty over what is the right architecture to fit your data, not just what are the right weights of this particular architecture. And with PFNs, you could also do that. You simply have a prior over different architectures. And then for each architecture, you have a prior over the weights of that particular architecture. And then you just integrate over all of that in a forward pass. So you kind of get the result of running a Bayesian neural architecture search, except you don't get the posterior over which is the right architecture. It's just the distribution is the integral over all the possible architectures that could have caused this data and their weights. And with MCMC, you would have to do reversible jump MCMC, like something really complicated in order to get there. All right, so this is PFNs. There's been a lot of different follow-ups of PFNs. This is sort of an old slide. There's a lot more follow-ups now. But in particular, there's tabular data, TabPFN, that I will talk about. There's forecast PFN, which was an early work for time series. There's other domains. So we have PFNs have been applied to BO, there's also medical imaging, genetics, etc. So PFNs are cool. I very much recommend checking them out. Yeah, BOPFN. So can we replace the GP in Bayesian optimization with in-context learning? Yes, we can. And the biggest flexibility here is that the biggest plus is the flexibility. So if you might have heterogeneous noise, or you might have change points, or you might have just really heterogeneous data with different types of data distributions or whatnot, just put it in your prior, and that's kind of all you need to do is simulate data with these properties from your prior, fit a PFN for that, and then you get a posterior predictive distribution under those particular assumptions that you put in the prior. And there's just kind of no math that you need. Just as long as you have a mechanistic prior to sample from, that's all you need. We have also applied this to learning curve extrapolation. This is sort of the first master thesis I ever supervised. Actually did MCMC in order to extrapolate learning curves using a prior over increasing but stagnating functions. And this work here is sort of 8 years afterwards, then did that in a forward pass, like 10,000 times faster. And yeah, it's kind of neat that you can do this. And then, of course, we combined these two in order to also do Bayesian optimization with learning curve extrapolation, sort of in a freesaw Bayesian optimization style. So there we have a basically a prior over how the hyperparameters cause different learning curves. And yeah, then given multiple initial learning curves like these here, different models extrapolate them differently. And yeah, we argue why these predictions here would be the best in the paper, and also quantitatively do so. But also in the end, they lead to the state-of-the-art freesaw Bayesian optimization method. All right, that was a flyby of PFNs. I would like to get to TabPFN, so necessarily this was somewhat short, but there's one question by Z. Could you comment on the trade-off between computational cost and the performance of the PFN? So, well, the computational cost is mostly for training the PFN, and well, it gets better the longer you train, just as sort of usual in foundation models. At some point, you get stagnating improvements. And there is, of course, an overhead in inference time that is quadratic right now. And well, if you have a really big PFN with a lot of layers and so on, then of course the computational complexity is linear in the layers, and so also in your inference time. But by and large, it's most of the time is in the pre-training, and the pre-training is actually not that bad. It's most of these models here, the pre-training takes a couple of hours. So it's actually not horrible. For TabPFN, the pre-training then took like 2 weeks on one machine, but so also not crazy. All right, so TabPFN, let's get back to tabular data. So tabular data, as I mentioned before, extremely widely used. And we try to learn a mapping from X to Y. So I'll represent that as there's X train, Y train, X test. And this is a question mark. We want to predict the Y test. And we do care about this long tail of small data sets. There's a lot of data sets in tabular data that are very small. And it's very different than in images, where you can have something like ImageNet, where there's all kinds of different images, outside, inside, whatnot, together. Here, if you have a data set from, I don't know, finance and one from medicine, they have different columns, they have different semantics. It's just very hard to get any positive transfer. And that's why it has really been a problem that was elusive to deep learning so far. Deep learning didn't actually traditionally do well on it. And instead, we're still using gradient boosting methods from sort of 20 years ago. And people also still use random forests, etc. Neural networks, on the other hand, they excel when you have large data sets and are prone to overfitting on small data sets. And TabPFN sort of turns that around. It's particularly good on small data sets and is very fast to train. But actually slower to predict than XGBoost. So it's really sort of the opposite. So yeah, TabPFN is this first state-of-the-art deep learning method on small tabular data. We pre-trained it on 130 million tabular data set. And it clearly is the best tabular method now for small data sets. So what we had in the Nature paper is up to 10,000 data points and up to 500 features. So that's where we verified that claim very solidly. All right, what is TabPFN? So it's this learned algorithm for small tabular data. I mentioned earlier that it's very hard to get positive transfer between these different domains, but what you can do is actually learn an algorithm that transfers across these different domains, and it's an in-context learning algorithm that is being learned. So you could frame this as next word prediction, where in comes the features x1, y1, and then xn, yn, and then come the features for the test data point, xn plus 1. Question mark, of course, you want to predict the yn plus 1. So we could do this auto-regressively. In the end, we don't quite do it auto-regressively, but it is similar. To be more precise, however, of course, we have a set, not a sequence. And to be even more precise, we want to have the probability for yn plus 1. So this PFN does all that in a forward pass. How does it do that? Well, it has parameters, theta, and these thetas are just trained to minimize across entropy loss across data sets now. So previously we had functions and samples from these functions. Now we have data sets and data points in this data set. Which data sets? That's a big question that arises because we don't have trillions of data sets, and the data set is going to be a token. We have millions of synthetically generated ones. And how do we train it? Really, then it's just a standard transformer architecture, dropping the position and embedding, as I said before, and train it with standard supervised learning. So the question is all about the prior again. Here pictorially again, what TabPFN does. So we sample xtrain, ytrain, xtest, and ytest. Take out the ytest. I have a question mark here. This goes to TabPFN that makes predictions. And then we look at how likely is this ytest under this prediction, compute the cross entropy. And that's one data point to do backprop on. And we do that over millions of sampled data sets. And then once we've trained a TabPFN, we actually have it here, and in comes the real data, and we make predictions for this actually truly unknown question mark here. So in the end, it's kind of clear that this works with backprop, except it's a question that's purely for classification, correct? Hence the cross entropy. Actually, for regression, you can also have cross entropy. It's just sort of quite similar to RMSE there. But so for regression, it's really pretty much the same. And then the uncertainty for regression, again, we have this binning distribution. And so you can compute means and variances and kind of any property. You could even compute EI, etc., directly from this bin distribution. So the distribution is truly like this, it's multimodal. But so the only missing piece is, how do we actually generate synthetic data sets that resemble the data sets that we actually expect? Because TabPFN will then approximate the Bayesian posterior for that type of prior. And if that prior, if the data sets we get are exactly from the prior, then we do the optimal predictions we could for these data sets. All right, so how do we sample this prior? We integrated principles from causality. So we sample and initialize a causal graph. Then sample edges in this graph, sample where is the x, where is the y. So we don't say that the x has to cause the y. It could also be the other way around. We sample edge weights. And then there is also these particular special variables that are at the root nodes. These are noise variables. And so this here is the equivalent of a function before, and these are the equivalents of data points sampled from this function. So we sampled 3 data points. We sampled them by sampling the noise variables and then deterministically forwarding them through the computational graph, and then just reading out where is the x1 here, where's the x2, where's the y, and we do that 3 times. And then we have 3 data points. And if we want to have a classification, we also sample some class determined class boundaries. And then we have a classification data set here, one data set with 3 data points. And we do that millions of times, sampling thousands of data points. All right, a question in the chat. What is the value of using the transformer here? Where there is a single label to be predicted, it wouldn't get any advantage for during training. Why not use any permutation equivalent model like deep sets? Yeah, you could use deep sets. They haven't been better for us, so we use the transformer, but maybe you can get deep sets to work better. The prior had another thing here where we want to actually not overfit, and so we actually want to reward the simplest explanations possible. We can, so we do have structural causal models like this in our prior, where we have lots of latents and very complex multi-node, multi-layer architectures. But the more likely are these simpler ones where you have just exactly the y's and the x's you need. And that leads to this prior for pretty simple functions and sort of a Bayesian Occam's razor. In the end, the generated data sets then look quite similar to real data sets. So here are synthetic data sets, here are some real data sets. And when you have sort of solved machine learning for millions of these synthetic data sets, then it sort of makes sense that you've learned an algorithm that if it can solve these millions of data sets, that it can also solve data sets like this and make predictions for them. And it aims to make, and since it's optimized with cross entropy, it tries to actually make very smooth predictions and to not be off too much, because mispredictions that are quite certain are penalized heavily. And that's why it ends up with pretty smooth predictions here, in contrast to, for example, things like the more tree-based algorithms like boosting. All right, so that's a quantitative result. It's also super simple. I kind of played a big role in coming up with this or setting up this field of AutoML. And we had this auto-sklearn method that is just somewhat complicated in the end, right? You have this big machine learning pipeline with data preprocessors and classifiers with hyperparameters, and then run wrap Bayesian optimization around it, do some meta learning, build some ensembles, and then you end up with a lot of lines of code. And that's sort of hard to maintain. This here, it's a TabPFN forward pass. You can encode this TabPFN in Onyx, and then you have a sensor that's actually running an AutoML system on there. So it's actually kind of cool to have this flexibility. And no worries, those of you who like AutoML like I do. AutoML will make a comeback in a couple of slides, so it's definitely we need it in order to get top performance. Quantitatively, in 2022 already, we got like in 1 second, we were better than AutoScaLearn was in an hour. So 3,600 fold speed up on the CPU. If I have a GPU, it's also 36,000 times. This is, of course, on average and not on every single data set. And in 2022, we had lots of limitations, in particular up to 1,000 data points, up to 100 features, up to 10 classes. And we didn't yet optimize for categorical features, missing values, uninformative features. And we only did classification. So sort of all the stuff you need in order to do data science, we kind of didn't do. And that's why it was sort of a proof of concept. And what we've done in the meantime in TabPFN 2 is to just fix all these issues. So we scaled up, not arbitrarily, but at least to 10,000 data points, 500 features, Nobody has asked for more classes really. But now we also do categorical features, missing values, uninformative features, and also regression. And we reduce the inference time by some KB caching. All right. Yeah, what did we do? So we scaled up using more efficient attention and a change in architecture, and then these inference speedups. And a lot of time went into better priors. So we used trees in the structural causal model, support different activation functions, discretize categoricals already natively in the prior so that it really learns more about categorical values. And we also demonstrated foundation model capabilities. The new architecture does some axial attention. So you have one attention that's across features and then an attention that's across samples. And then there's a standard MLP, and you do this 12 times. And then from this final value, you read out this Riemann distribution with an MLP. And so this architecture here allows us to train up to X data points, but then test on more data points than we trained at. So actually, the model that's evaluated in the Nature paper never saw more than 2,000 data points during training, and we evaluate up to 10,000 data points. And likewise for features, TabPFN 1 actually had an architecture where it was limited a hard limit up to 100 features. Here we have a soft limit now to 500, but if you have 600, throw them in. It would just generalize, just like standard transformers generalize to larger contexts. All right, in terms of quantitative results, so yeah, we have here linear regression, MLPs, SVMs, random forests, different boosting methods. Actually, we don't have GPs, should have GPs, and TabPFN. And yeah, you see that the boosting methods definitely do well. We have the dark blue is the default, and the light blue is with 4 hours of tuning. And yeah, so without any tuning, it in 5 seconds does better than 4 hours of tuning, which you also see in this graph here. And yeah, so in one data set here out of the 29, it's still worse than CutBoost, but on 28, it's better. And so in general, yeah, after tuning, CutBoost sometimes also gets a bit better, but TabPFN also gets often much better. For regression, we have similar results, but not quite as good results. So I mean, still the default is better than the tuned methods on average, but you do see more points here and more points here. And yeah, then we also compared to AutoGluon, which is definitely the best AutoML system on the market. So AutoSKlearn 2, we sort of stopped at some point, and AutoGluon integrated all the cool things of AutoSKlearn 2 into AutoGluon. So there's really no need for AutoSKlearn 2 anymore. AutoGluon also has really good assembling in there, and we actually pulled that over to TabPFN to do this post hoc assembling in TabPFN. And so for classification, actually, the default of TabPFN was already better or as good as AutoGluon with 4 hours. But then with this post hoc assembling on top, it gets yet better and has this win ratio of 75% to 25% roughly to AutoGluon. And for regression, there actually, yeah, the default is not as good as AutoGluon. AutoGluon is definitely better when tuned. But with the post hoc assembling, we still get the win ratio of 70 to 30 for TabPFN. All right, some ablations and informative features. So here, that is something that TabPFN 1 really struggled with, and that MLPs are really poor at. So here, for each feature, we add 9 noise features, and yeah, the MLPs then really crash in performance, but TabPFN now doesn't care much anymore. Even with these noisy features, it's still better than CutBoost without the noisy features. And we just got there by telling the prior that there might be uninformative features. There is a question in the chat. What are the improvements that were made for handling categorical features in V2? How the win rates calculated? Well, that's sort of the standard way, like 10-fold cross-validation, 29 data sets, so there's 290 races to be won, and 70 are won by TabPFN, and 70% by one and 30% by the other. And the improvements for categorical features was really, mostly telling the prior that there's categorical values around. And also this axial attention actually really helps for categoricals. Here's the ablation for missing values that doesn't matter anymore for TabPFN because the prior knows that there might be missing values and the prior knows that there might be categorical. So this is not, this is the data sets without categoricals. This is the data sets with categoricals. So this is not a direct comparison. But yeah, so you can't compare this blue against this blue or something like that. But yeah, it by and large, it just also now works on categoricals. And in particular, it does work well with less samples. So you can compare this blue against this blue. This is 50% of the samples. This is 100% of the samples. And TabPFN with 50% is as good as CatBoost using all the data. All right. In terms of explainability, well, it is a black box method. It does in-context learning. So it's very hard to interpret what exactly it does. But we can do all kinds of post-hoc analyses, including, for example, SHAP analyses. And here we have the SHAP analysis for linear regression. That actually is very interpretable. You see a clear linear trend here. And with something like CatBoost, that has such rugged predictions that it actually, the SHAP values kind of get lost. You don't really see much anymore. But with TabPFN, because it's smoother, the Shapley values are also much closer to the ones of linear regression, while also actually just making much better predictions than linear regression. All right. And then, well, TabPFN is a foundation model, so you can also do fine-tuning of it. It's pre-trained on large amounts of data, just like your llama would be, for example, and you can fine-tune it to your own data. So it's really, there's this clear analogy to other foundation models. And for us, our own data would be data sets with different properties. And so if you have a data set, in this case here, there were a couple of data sets that were just sine waves. And the test data set then is a sine wave here. There's just the yellow points are seen by the model. And it, of course, doesn't know that it's a sine wave and then makes some errors. And if you fine-tune on sine waves, then it gets much better. So it still makes some errors, but it, by and large, is just much better. And so in contrast, you just can't do this type of fine-tuning with traditional tree-based models, for example. All right. So that was TabPFN v2. The rest is relatively quick. So how do we apply this to time series? Actually, it's very direct. We just featureize a time series. So like we just look at this time series, we featureize it as this, each of these time steps becomes a data point where the X values are the running index, and then the year, the day of the week of the month, the months of the year, etc. And then at test time, you can have, for example, 17 steps ahead. That's just one row here. And so you can directly predict ahead as far as you want. It's not autoregressive. So yeah, you have X train, Y train, X test, question mark, feed that to TabPFN and get predictions. And actually, this simple extension achieves state of the art on this most common benchmark for time series. It's called GIFT-eval. It's a tiny model compared to this TimesFM and Chronos. And is only trained, again, it's the same model as in the Nature paper. It has only ever seen synthetic tabular data. Has never seen a real tabular data set. It has never seen a time series. Has never seen the particular encoding we use for this time series. So for me, that just goes to show that there is a lot to be gained in time series forecasting. And we're very excited to be working on that more. Some exemplary use cases. So we've used this together with our partners at Tactile they have a risk decision automation platform. They use it to enhance fraud checks and credit risk anomalies. So they have TabPFN on their platform now. And they also saw that particularly for small numbers of data points, for your particularly odd transactions that actually require manual intervention, they only have a few data points, so traditional methods don't actually work well, and TabPFN works a lot better for them. And yeah, for credit risk and anomaly detection, they basically just do a forecast, and then if the actual measurement is off the forecast a lot, then that actually warrants looking into it a bit more and could be an anomaly. Another fielded application is at a company called Boston Gene that has a machine learning powered blood test and analysis platform. And they report that, the data scientists are just 10 times more efficient now. So they save 90% of the time while actually getting a 53% error reduction, getting ROC up from 0.81 to 0.91. And so in general, this just enhanced their efficiency and allowed them to actually work on stuff that they want to work on rather than doing hyperparameter optimization, etc. All right. Then there's large interest from hedge funds where I can't talk about. But if you can predict the stock market, you can, of course, think that this is a money printing machine. And then, it's really easy to use now. There's a Google Sheets integration, and we built open source, and the open source community just builds on top. So this is really cool. Someone in the community just made a Google Sheets plugin, and we have this running in Google Sheets now. So really cool to have the open source community. Some extensions. So we do have foundation model capabilities. We can do prompt tuning. This was in Europe's paper in 24. We have like little teasers of data generation and density estimation and outlier detection already in the Nature paper. And we have various extensions to drift resilient. TabPFN actually looks at data drift and sees that there's different, you want to make different predictions if you expect that there is data drift. We're working on a counterfactual fairness. There is very cool work by Andreas Müller on actually having a hypernetwork that in the end actually outputs the weights of an MLP such that when you feed the X test into this MLP, the Y test is good, and you can backprop through all of that. And the performance is not quite as good as TabPFN, but it's super fast. It just outputs an MLP, and you don't have to worry about inference time anymore. And together with Andreas, we extended that to output a GAM, a generalized additive model, where inference is really O of 1 or O of number of features. You just look up for each feature in the score function, what should actually be the additive term of this feature. And so there, instead of outputting the weights of an MLP, you just output the weights of a binned score function. And it's super interpretable because it's just, for each feature, you just look at, okay, if this was lower, well, my score would be this. So it's just directly interpretable. And Rich Karana is also on this paper. And actually the idea came from Andreas and Rich, and I'm super excited about it. All right, now we also support textual features. This is, of course, quite simple. We just run text through an LLM. But the cool thing is that actually the featurization by an LLM, just TabPFN just directly understands it and gets better with it. So there's no fine-tuning going on here, actually. That's quite nice. Wasn't entirely clear that this would be the case. And I've seen many people saying, oh it can only do 10,000 data points, so we'll subsample the data to 10,000 for TabPFN and use the original data for other methods. Don't do that, please. But there's multiple extensions we have. For example, you can just fit a little random forest that has TabPFNs in its leaves, and there's 10,000 data points in leaf, for example, then you can scale to arbitrary data. And here are some examples for 50,000 data points where, yeah, in this case here, it actually worked quite well already with a subsample, but in this case here, it worked quite poorly with a subsample and still nicely with a random forest. Of course, it's then more expensive because it needs to fit the different TabPFNs in the different leaves, but yeah, it definitely gets better. All right, some extensions in progress. So we're working on a model that can do 100,000 data points with a base model. We want to get to state of the art with 1,000,000 data points relatively soon. And yeah, also reduce inference time. We're doubling down on time series forecasting to actually do something that is maybe a bit more native and also support multivariate time series. And we're working on causality, so causal discovery, actually getting maybe posterior over the latents. And you also want to do an interventional version of PFN, where if you say, what if I change this variable, what will happen to this other variable? And we just can't just read that off the current PFN, of course, because yeah, that's an interventional query that's not in the training data. But if you put it into the training data, then yeah, we hope to be able to do that, and together with Bernhard. Yeah, so takeaways. TabPFN is a new default for small tabular machine learning and time series. Currently, up to 10,000 data points and 500 features. This claim is verified. The unique features are it's faster than previous methods, better peak performance, and it also works well with less data, more interpretable than some tree-based methods and existing applications in finance and some other methods. And the cool thing is you can fine-tune TabPFN to your use cases. And it's open source under permissive license. It's sort of Llama-like. So it's Apache +1 clause that says you have to say built with TabPFN, so that everybody sees it's TabPFN and not some competitor's product. All right, with that, thank you very much. Oh, and one shameless claim. We're hiring, we're funding. So please tell all your friends. If we hire your friends, you get $2,000. And
So
there's some questions in the chat. Should I go through
I'd
those?
also just like to make a short kind of end of talk announcement, which is that we're going to have two parts for the question and answer period. There's going to be a period of questions that are live streamed, and then following that, we will conclude the live stream for those that prefer not to be recorded and just continue the discussion on Zoom. And you can, as people have been doing during the talk, use the chat to ask questions. So back to you, Frank.
All right. Yeah, thank you. At some point, I stopped looking at the chat, so I'm going through the history. So is the same model used for both regression and classification, or it requires different output heads as the number of bins would change? We actually do use the same number of bins, but we use slightly different priors. So it is different models in the end, but it's really, yeah, very much the same methodology. In TabPFN v2, how do you convert each feature into vectors before feeding into transformer? Are all features, numerical, categorical, input, target, dealt with the same when converting into vectors? Yeah, this is sort of the simplest thing we can do. Numerical, we just multiply them with an embedding matrix. And categorical, yeah, they're basically the same. So it's one hot encoded and then multiplied by a one, by an embedding matrix. So really, I'm sure one can do better. There's a lot of different works on better embedding methods. We did play around a little bit with some. They didn't make things better. Maybe in combination, the results would be different than in the original papers. But we did not benchmark this really deeply, but just went for simplicity. All right, can you send the Google Sheets link after the talk? Yes, I can. One disclaimer. So this was actually what has been built was one pre-trained TabPFN, and what you saw in the demo was just the inference. But yeah, we can do the same actually with also the training, because training and inference actually cost the same amount of time. So we're making this a little bit nicer, and it's on our website then. What if a different architecture rather than transformer is used? Does it impact the performance much? I can't say much. Sam very early on tried MLPs and they were worse. That's all I can say. And we just use transformers because, yeah, with cross entropy optimization of this binning, it's just it's a classification problem. So it's regression as classification as well. And for classification, transformers are just really well tuned. But very likely you can get some other architectures working. We tried Mamba a bit. Mamba didn't work so well, but that might also be transient. All right. Was the model retrained on additional synthetic datasets containing text features, or did it perform well on text features out of the box? It was the original model. We did not touch that. It's really, we just pushed the text through an LLM, got the features out, put it in TabPFN, and it worked. And I found that somewhat surprising. Was a model, sorry, that was a question before. You mentioned extensions to recommender systems. Can you say more about that? I've been trying to learn a latent utility model from preference pairs. Yeah, I can't say much more about that, not because it's private, but because we haven't really looked into it that deeply. But it's, tabular data, it's sort of just another application of that. And so, yeah, maybe drop me a line afterwards. Do you have any intuition as to why the priors designed for tabular datasets work so well for time series datasets and even better than the models that are trained on time series? Not a whole lot. I mean, it's structural causal models, so I just can only assume that, well, causal patterns, like basically you can interpret what TabPFN is doing as getting your posterior over what is the right structural causal model to explain this data. So for each structural causal model, you would make some predictions and you would say how likely is a structural causal model for your data, and you do the Bayesian integral over all of them. That's sort of what it's approximating in a forward pass. And you can also do that for time series. Why does it work so well with this particular embedding? There are like signs in the activation function, so it can get these patterns that are repeating, but we haven't understood deeply why exactly it works so well. So we're studying this a bit more actually right now. Are there plans to update the open source repo to have support for incorporating LLM embeddings in the near future? We're thinking about it. It's annoying to have to deal with API keys and so on. So we haven't looked into it that much yet. That's why it's only in the API. Can PFNs update their prior assumptions after obtaining new observations? For example, if the prior changes as you require new data, the PFN's training data may no longer align with the updated prior. Yes, indeed. And we would just tackle that with fine-tuning. So yeah, you fine-tune your foundation model with data you have that doesn't directly match the original pre-training data, but the original pre-training still helps. And yeah. Second part of the question, or perhaps can PFNs dynamically switch between multiple pre-trained priors, for example, through mixture models without retraining? Yes, this ought to be possible. And indeed, I mean, this PHE part, the post-hoc ensembling, that is ensembling different versions of TabPFN. So it's actually, there's, I think, 3 classification PFNs and 4 regression PFNs that we had laying around, more or less. And we assemble them with a post-hoc assembling, slightly different architectures, slightly wider, etc. And that already works. And well, and if we had like different priors for each of them, they would become more different, and that would help more. So definitely together with your assembling, that would be good. And yeah, also mixture models would also be a good idea. Have you tried to normalize the data before input into the model? we have not only tried, we do that every single time. So yeah, so like the data comes, we first normalize it like a 0, 1 normalization, and then feed it to the model because otherwise, scales differ. Sometimes it's like 10 to the minus 13 meters, like nanometers or whatnot. And sometimes it's very large numbers. So like that would be, yeah, too hard for the neural network to have to deal with that. But if you just normalize it, it would be much easier, and much more data efficient to train. All right. Can you recover the SEMs? The SEM generated synthetic data sets that most align with inference data set in a sense, proposing high probability causal mechanisms that potentially generated the inference data set or a mixture of them. We want to do that. We haven't done it. It's yeah, would be really cool. It is not trivial because, well, it's not trivial in the existing mechanism because we have this bin distribution over one-dimensional output. And if we want to represent the graphs, the structural causal models, etc., then we would need to have a probability distribution over the graphs, and then it gets a bit more hairy. We're looking into it, but have not published on that yet. All right. Any more questions that are live? I think I'm through the ones in the chat.
I guess on this note, because I don't see any further questions in the chat, perhaps now is a good time to move on to the next phase of the discussion. And for that, we will now conclude the live stream. And before I do so, I just want to thank all of our listeners on YouTube for joining us today and remind everyone that we have another seminar coming up next week. And you can check out the schedule on our website, which is gp-seminar-series.github.io. And please feel free to check that out and sign up and